You didn't do the reflection, you still can until like Thursday. So even if you're not enrolled, I would appreciate everyone doing it so I can know whose class you're in, know where you're from, know what name you like to be called. I was gonna try and learn some people's names. It always seems challenging in a situation like this, but we'll see. What else? Oh yeah, I know what I was gonna say. If you're in Alvarado's class, not enough homework. You're not going to learn anything if this is all you do. So I would encourage you, if you're in Alvarado's class, at least, I mean, maybe future assignments will be longer, but 4 problems for a week, it's not enough practice. You're just not going to learn really enough if this is all you do. So what I'm thinking I will do is I will post the homework assignments from the other 2 classes, all 3 classes actually, on Canvas, just because that's easy. And I will probably try to seek out some other homework as well. Not that you obviously, I'm not going to make you do anything, but right, it's on you to do it so that you learn it well enough so that you understand it. But again, I can't say enough. This is not enough, right? You're just not going to get enough practice if this is all you do this week. On the other hand, why can't I remember his Goldsmith, yeah. His homework assignment is a little bit of review. That seems sufficient. And then Lee's homework assignment, which is just problems from the book. Well, not just, I should say, is problems from the book. I think also looked like it was, I mean, you could always do more, right? I mean, that's always true in math class. You could always get more practice. So I would encourage you to try to do enough until you feel like you're understanding it. And if you're looking for more practice, I can certainly find you more practice. I can pick out problems from the book just as easily as anyone else. I also have other sources. So maybe I'll just do that anyway. I might just go pick out some problems from the book and say, you should do these problems. And if you really, really want, I would be happy to grade them. I don't have to, but if you're looking for some feedback and you did some homework problems and you want some feedback, I would try to grade them as quickly as I can. So if you're looking for that, that is an option. You're welcome to hand in papers to me anytime you want. Be like, James, I did these homework problems. Would you grade them? Like, yes, I will. And I will get them back to you in a couple days. Maybe faster. All right, it's 2:10. Before we get going, questions, comments, concerns?
If we do our homework on our iPad, can we like submit it can we just send it to you in an email and you could check it?
Totally, that'd be great. I'd be happy to do that. Yes.
Thank you.
So I should say specifically, I mean class, because that's going to be graded by someone else. But if you want more practice, I am happy to grade additional problems. If it's your actual homework assignment, I'm happy to like look at that with you or help you with that. But I'm not going to grade your actual homework assignment that you're turning in. Because every class is submitting homework, right? No one's like, no, who's not? Lee's not. Okay. For Lee, I'm happy to. The other 2 classes, your actual homework assignment, someone else is going to grade that. It doesn't make sense to duplicate that work. So I'm not going to do that. But yeah, the other thing I was going to say is if you are in 16B, it is totally fine if you are here. Also, Claire, who teaches the actual Co-16B class, even if it is a time that doesn't work for you, which is, I believe, is the hour and a half before this, but I'm not 100% sure on that. She said she does record her lectures. So if you want to see what's happening in that class as well, I really do encourage you to do that if you're in 16B, just because it's going to be a better fit. At the beginning, it might be similar-ish as far as the pacing and stuff, but eventually we're going to diverge quite a bit. So if you're taking 16B, I really can't encourage you enough to check out Claire's class. Also, Claire is a lovely person and she is a great teacher. So you'll be missing out if you don't, I would say. Not that I'm not good, but Claire's pretty great. Would you be able to make some web work problems? I don't know I never have. So I don't know if that's something I'm able to do or not. I will look into that. Actually, I will ask Claire about that because she knows more about that than I do. So I'll try to do that because that would actually be really nice if that was possible, because that way you don't have to wait for someone to give you feedback. You can just try to do the problems. So yeah, let me actually write myself a note here. I feel like I should be able to, but it might require like having the book for the class as like be part of the class, and that's not something we have. So, but we will try and find out, because that would be ideal, I think. Actually, good question. Thank you. Other questions? All right, let's continue talking about Riemann sums, which hopefully Lee's class is going to get to very soon if he hasn't already. Yeah, we should do this example. So let's say we want to, and this time I'll actually show the applet on, so everyone can see it, people on Zoom as well as people in class. Let's find, or let's estimate the area under the curve f of x equal to, what have I got here? Yeah, let's write it like that. 30 minus x minus 3 squared on the interval from 0 to 8. Using, I will point out, it's pretty typical when you're doing this by hand to use like 4 intervals or maybe 6 or maybe 8. But once you start using a lot of intervals, it just becomes a complicated computation. So we're going to use n equals 4. That's not to say that you can't use more. It's just very typical for us to use 4 when we're doing it by hand. And we're going to do this. We're actually going to talk about how you would do this all. Well, there's actually more than 4, but we'll talk about the 4 kind of typical ways. So let's first talk about it using right-hand endpoints. Let's draw ourselves a little bit. So 30 minus x minus 3 squared. It's a downward opening parabola. They've actually told us where the vertex is as well. The vertex is when x is 3 and f of 3 is 30 minus 0, which is 30. So I'm going to give a quick sketch of this. Let's see. So I know if I plug in 0, 0 minus 3 squared is 9. 30 minus 9 is 21. So 21. And then I know I'm going to break this up into 4 equal sections of length 2. It's going to look something like this. When I plug in 3, I get 30. When I plug in 6, I get 21 again. When I plug in 8, I get 5. That sounds nice. That's my not very good graph. Okay. Pens, more pens. So if we're using right endpoints, well, here's how we're going to write. Question. Oh, no. Okay. You're like, can you see that? Can you guys see that all right? Okay. I feel like this light here is not super helpful. Let's find out. Yeah. Is that better?
It doesn't change it.
Can I turn like half the lights? Is that better? I think that's better. Okay, we'll try that. In the dark, I feel like people are just like, I would fall asleep personally if it was me. So like, I don't want to be all in the dark. So let's see. So we're trying to estimate the area using right endpoints. We're going to call that R4. And again, it's just a bunch of rectangles. So I've got 1, 2, 3, 4 subintervals. And my delta x, which is my b minus a divided by n, which in this case is 8 minus 0 divided by 4. That's just the width of each subinterval. So that's going to be the base of each rectangle. And then for my first rectangle, between 0 and 2, I'm going to use the right endpoint to find the height. So there is my first rectangle. The height's going to be the base, which is 2, times the height, which is f of 2. My next rectangle. The base is the same. The height actually is also the same because f of 4 happens to equal f of 2 here. In the second rectangle, I'm plugging in 4 to get the height. My height is f of 4. And we just keep going this way. The next rectangle, the interval between 4 and 6, I'm using 6, the right endpoint, to find the height, which is f of 6. And finally, for the last one, I know I drew it kind of jankily here, but there's my height at 8. So f of 8 is my height. So that's how we're estimating the area under the curve. And it's not a very good estimate. I can't even really tell if it's an underestimate or an overestimate. It's probably an underestimate if my graph is anywhere close to being right, but I don't know. Let's actually calculate it just so we can have some numbers here. This is going to end up equaling 2 times, okay, so the quick math here, f of 2 is going to be 30 minus 1. F of 4 is going to be 30 minus 1. F of 6 is going to be 30 minus 6 minus 3 is 9, is 3, sorry, 6 minus 3 is 3, 3 squared is 9, 30 minus 9 is 21. And finally, f of 8 is going to be 30 minus 8 minus 3 is 5, 5 squared is 25. So 30 minus 25 is 5. And then we can calculate this. It's going to be, I don't know, something here. 50, 79, 84. I feel like I wrote the wrong. No, that's right. 168. Question.
What does delta x stand for?
Delta x stands for the width of each subinterval. So the length from 0 to 2, 2 to 4, 4 to 6, 6 to 8. Each of those widths of our rectangles is going to be 2 in this case. And in general, the way you find it is by taking the total length from 0 to 8, so 8 minus 0, and you divide it by the number of intervals, which is 4 in this case. But it could be anything. Does that clarify things? Cool. All right, let's find the other 3 things we're doing, because I definitely saw that Alvarado talked about this briefly. There's 4 different ways you can kind of talk about estimating the area under the curve. So we could also do this using, in fact, so I'm going to be a little bit smart about this. Maybe I might try to be smart. Let's do L4. And instead of drawing the picture again, let's just think about, well, instead of using the right endpoints, which are 2, 4, 6, and 8, now we're going to plug in the left endpoints, which are 0, 2, 4, and 6. So L sub 4 is again going to be our delta x times our f of 0 plus f of 2 plus f of 4 plus f of 6. I'm going to draw the picture here just to kind of make it look neat. So here's our f of 0 in red. Here's our f of 2. Here's our f of 4. And here's our f of 6. The red certainly seems like it's probably going to be an overestimate. Not 100% sure, but it could be. So we're going to get 2 times f of 0 is 21. F of 2 is 29. F of 4 is 29. F of 6 is 21. And we're getting exactly 200. Okay. And I would say, in my opinion, these are the typical ways of estimating area under a curve using rectangles. You're either using left endpoints or right endpoints because it's convenient. It's always easy to find the left endpoint and to find the right endpoint compared to the other 2 things we're going to talk about very, very briefly. You can also do this finding what's called the upper sum. So the upper sum is going to be the area of the rectangles with essentially the maximum height in each interval. So let's draw it one more time. And I said I didn't want to draw it one more time, but then I decided to draw it one more time. So here's our picture. All right, so the problem with this is it's not always easy to find the place where you have the maximum. In this particular example, I've cherry picked it, so it is, but a lot of the times it's not. So if I want to find U4, well, again, I'm just looking at each subinterval and finding the highest rectangle now. So for the first subinterval, I'm going to use the left, the right, or something in between. If I want to find the highest rectangle. Who thinks left? Who thinks right? Who thinks something in between? It's definitely the right, because at least from 0 to 2, at least if you believe that my drawing is correct, from 0 to 2, the highest point is the rightmost point. So there's our rectangle. That's going to help us find the upper sum. But now from 2 to 4, the highest point isn't the left or the right. It occurs when x is equal to 3. So we have to draw this rectangle here. And then for the next one, it's decreasing after that. So the highest point is when x equals 4. I know I've drawn this not particularly well. And then finally, the rightmost rectangle here, the highest point is when x is equal to 6. So our U4 estimate of the area is once again, get your delta x, which is just the base of each rectangle, and then you're multiplying that by the heights of each rectangle. The first rectangle has a height of f of 2. The next one has a height of f of 3, and then f of 4, and then f of 6. So that's going to be 2 times f of 2 is 21, f of 3 is 30. What was the function again? I know here's the function again in case you didn't memorize it. Why would you memorize it? I wouldn't. 30 minus x minus 3 squared. So f of 2 is definitely not what I wrote here. Good thing I went and checked. F of 2 is 30 minus 1, which is 29. F of 3 is 30. F of 4 is also 29. And f of 6 is 21. If you add those all together, assuming I did it right over here, I did, cool. You get 218. And in a similar way, you could do the lower one, but I don't want to do that because it's tedious. But what I do want to do is I want to show you all again the applet I talked about last time so that the people on Zoom can see it as well. If I can do this real quickly here. So let's take a look at this briefly. I think it's neat. I think if you're looking at Riemann sums, this is worth your while. So let's go ahead and just check this out. If we want to look at the function 30 minus x minus 3 squared. Let's zoom out. Can I zoom out? Maybe. Can I zoom in? Sure. So there's our function. It's pretty big. I should change my interval before I get too crazy here. I want to go from 0 to 8. At 8. It's hard to tell. I want to be right on 8. There we go. And then we're going to change the number of, gosh, I want to see the whole thing. Okay, there we go. So number of subintervals was 4. And then we can use right endpoints and get 168, like we did. Or left endpoints and get 200, like we did. Or we can even go, I think, upper. And it shows us the upper of 218. Or we can go lower. And it shows us the lower of 152. I must be off somewhere where I've placed a point here. Should be 152, right? Yeah, 152. So again, I think that's kind of useful. And then I will point out one more time. As you let the number of subintervals get larger and larger and larger, the error gets infinitesimally small. And it doesn't matter if you're using the lower sum or the upper sum or left endpoints or right endpoints. You're getting really, really close to this number here, which looks like it's, I don't know. I mean, there's still a little bit of error, right? Because it's not an exact calculation, but we're getting closer and closer to something between, I don't know, 187.9 and 190.68. So we're pretty close. And eventually we'll figure out how to find the exact one. Okay, so where to go next? So here's the idea, is that we actually are going to do that. We're going to take these Riemann sums and we're going to find the limit as the number of intervals gets larger and larger and larger. And the question always becomes, how much detail do we really want to get into here? Well, we'll try to be not too much. This class always kind of straddles the line between a lot of detail and a little bit of detail. But let's look at least one example here. So Come on. All right. So here's what I would say. To get the exact area under a curve, which you will often draw like this. So here's your curve, f of x, and you want to find how much area there is on the interval from A to B. We draw it kind of like this. Here's what we do. We let the number of rectangles that we're adding up I should say the number of areas of rectangles, but you get the idea. We're adding up, get infinitely large. So the idea is that this expression, the integral from A to B of f of x dx, all that means, when you see that, all you should think of is, oh, it's the area under the curve. That's all that symbol means, is you want to know how much area is under the curve. Technically, it's the net area that is above the x-axis. So if you've got stuff under the x-axis, it counts as negative. But really, when we see this, we should just be thinking, oh yeah, that's area under the curve. And what we're going to see is that's going to equal the limit as n goes to infinity of all of the areas of the rectangles added up together. And there's a couple ways of writing this, but here's the nicest way of writing it. It's the summation from I equals 1 to n of the height of the ith rectangle times the width of the ith rectangle. So that's just the height. That's just the width. Questions or clarifications I can make, because I'm happy to clarify. So how are we going to do this? Well, let's look at some examples that are not terrible. For example, oh, I always hate my little cursor. Let me move this cursor here. Sorry. All right. So let's look at this example. We want to find the integral from 1 to 4 of 2x plus 3. And I should just point out, because we're going to see this a lot, when you see this here, what this really means, or at least what I think of, is when I see this symbol with this dx, these are just instructions that tell us to find the area. And eventually we'll develop a really fast way of doing this using antiderivatives and the fundamental theorem of calculus. But for now, we're not there yet. So we're going to use other techniques. We're going to use everyone's favorite, geometry. Geometry is great for finding the area under a straight line. So I'm trying to keep my notes in some semblance of the right order here. Maybe, yeah, okay. So let's graph it. So let's see, so y equals 2x plus 3 is a straight line. It's got a y-intercept of 3 and a slope of 2. So I'm not going to draw it perfectly, but it looks something like this. So 1, 2, 4. Let's see here. So when I plug in 1, my height is, let's see, if my y is equal to 2x plus 3 and I plug in 1, I get a height of 5. So that point there is 1, 5. When I plug in 4, let's see, 2 times 4 is 8 plus 3 is 11. So I'm trying to find the area of this shape here, which is a trapezoid. We can, excuse me, definitely find the area of a trapezoid. Or if you don't like that, because I've never really remembered the formula for the area of a trapezoid, let's just break it up into a square or a rectangle and a triangle. That seems way easier to me. So if we just cut this up right here, the area of this square, well, what's the base of that square? Almost. The base is 4 minus 1. And then the height of the square is, well, I cut it off right there, so the height's going to be 5. So that's going to give me 15 square units. And then for this triangle, well, the base is also 3. The height is, well, yeah, 11 minus 5, which is 6. And then for an area of a triangle, you have to do 1/2 times the base times the height. So we're going to end up getting 3 times 6 times 1/2, which is 18 divided by 2, which is 9. So the total area, or I should say the integral from 1 to 4 of 2x plus 3 dx is just going to equal 9 plus 15, which is 24. So this is a valid way of evaluating this integral. And in fact, on an exam, your teacher might sometimes ask you a question like this, or a question involving like an absolute value or a circle, where you are actually meant to find the integral by just saying, oh, I know what shape that is, and I can use geometry to find the area of that shape. That is a completely valid way, and sometimes the only way of finding the area under a curve. Questions about this before we do this the long, hard way? Which maybe is going to be terrible, but we're going to do it at least once because you should see it at least once. Okay, so we're going to draw it again, but we're going to draw it kind of really exaggerated so I can hopefully make the picture look somewhat decent. So let's try drawing this one more time. I'm going to draw it much less steep though. So here's my f of x equal to 2x plus 3. And let's say here's my 1. And over here, there's my 4. And I'm going to say that a is equal to 1 and b is equal to 4. Because typically when we think about integration, we think of the lower limit of integration as calling it a and the upper limit calling it b. Standard notation. So we're looking at this area, which I'm not going to shade in. So let's draw some rectangles. How many rectangles? More than 4, unfortunately. I would love to draw. We're actually going to draw n rectangles, which does not sound fun, but it's not as terrible as it sounds. So here's what we're going to do. We're going to do like, so here's my first rectangle, and I'm going to use right endpoints for my heights. Here's my first rectangle. Here's my second rectangle. And then I'm just going to do kind of like a, let's do one more, sure. I'm going to do like a dot, dot, dot kind of thing. Here's my ith rectangle. I have to label them here. Here's my first rectangle, my second rectangle, third rectangle, my ith rectangle, all the way to the last rectangle, which is going to be the nth rectangle. And just like before, we're going to find the area of each rectangle and then add up all the areas. So I'm going to call that R sub n. R for right endpoints, n for the number of subintervals. And just like last time, it's going to be the base times all the heights added together. So that's going to be delta x, which we'll find in a minute here, times. Okay, so here's the typical labeling that people start off with. Usually when we're breaking this up into n subintervals, we usually say that my first subinterval, the right endpoint, we often call that x sub 1. And the left endpoint, we call that x sub 0. And then we just increase the subscript. So this next one is, that's going to be x sub 2, x sub 3, all the way to in the ith subinterval, which side should be the x sub I? Should it be the right side or the left side? The right side, right? Just like for the third one, the right one was x sub 3. For the ith one, the right one should be x sub I, which means the left one should be x sub exactly. And then finally, for the nth one, the right endpoint is x sub n, and the left endpoint is x sub n minus 1. And b, so notably, a is equal to x sub 0, and b is equal to x sub n. It's just another name for the same thing. Okay. So now, if I'm going to find the areas, I'm just say, well, it's going to be delta x times f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus all the way to f of x sub I plus all the way to f of x sub n. And I'm not going to write it down, but I want to mention that if I was using left endpoints instead, I would just do delta x times f of x sub 0 plus f of x sub 1 plus f of x sub 2 all the way to f of x sub n minus 1 would be my last left endpoint. And just so you can see this written in the less, I don't know, there's a good word, a less terrible way. It's not the word I was looking for, but oh well. This is just the sum from I equals 1 to n of f of x sub I times delta x. Okay. Well, now we can actually fill out what things are. Delta x here is our b minus a divided by n, which is 4 minus 0. 4? Yeah, 4 minus, not 0 though. My left endpoint isn't 0, it's 1. My a value is 1, not 0. 4 minus 1 over n, which is 3 over n. And now for the x sub i's. So let's start writing some of these down. X sub 0 is just 1. It's our leftmost endpoint. It's our starting point. It's our a value, whatever you want to call it. And then our next x sub 1 is, well, I started at 1 and I added on 1 width, 1 subinterval width length, which is going to be my delta x value. So you can say it's 1 plus delta x, or if you prefer, you can say it's 1 plus 3 over n. And then the next one, x sub 2, I'm just going to add on another delta x. So from the beginning, it's 1 plus, in fact, I can even draw it. Oh, I can zoom in. I was thinking I can zoom in. I can say this here is just delta x. This here is just delta x. This here is just delta x. So x sub 2 is just going to be my beginning value 1 plus 2 delta x's, which is 1 plus 2 times 3 over n. And hopefully the idea is becoming somewhat clear here. The next one, I can put it down here. Yeah. X sub 3 is 1 plus 1, 2, 3 delta x's. So whenever I want to find the next x sub I, or I should say, when I want to find x sub I is just my a value plus I delta x's worth. I'm just adding delta x I times, which in this particular example is going to be equal to 1 plus I times 3 over n. Or I would probably write that as 1 plus 3i over n. Okay, I know it's a long journey, but we're most of the way there. So now we're going to rewrite the summation here. Let me zoom back out a little bit. So our Riemann sum using right endpoints with n subintervals is equal to the sum from I equals 1 to n of f of x sub I, which we just found x sub I to be 1 plus 3i over n. Excuse me, and our delta x is 3 over n. Okay, just a little bit more. So now we actually have to substitute in 1 plus 3i over n into our function. So f of x is 2x plus 3. F of this terribleness is going to be 2 times that terribleness plus 3. So we're going to rewrite this as the sum from I equals 1 to n of 2 times 1 plus 3i over n times 3 over n. And then we're going to need to take a break here for a second and do something else. But I'll say that our area, our integral from 1 to 4 of 2x plus 3 dx is equal to the limit, as n goes to infinity, of the sum from I equals 1 to n of this expression here. I forgot something though. You guys see what I forgot up here? It's easy to have missed because I wasn't being super clear. My function was 2 times x plus 3. And I missed the 2 times x. I forgot the plus 3 there. So this really should have said, it's not really a good way to fit it in here. So I'm going to make this look terrible. Plus 3. Sorry about that. Well, you can see it's 2 times x sub I plus 3, all times 3 over n. And that's what our integral is equal to if we take the limit as the number of rectangles gets infinitely large and each rectangle's width gets infinitesimally small. So we could write this. It's the limit as n goes to infinity of the sum from I equals 1 to n of 2 times 1 plus 3i over n plus 3 times 3 over n. Seems terrible. Unfortunately, in fact, just like some of you are in Goldsmith's class being reminded of the limit definition of the derivative, you learn it and then you kind of abandon it. In a similar way, this limit definition of the integral, we're going to see it like once or twice, maybe do a problem or two on it, and then quickly move on to the nicer way of actually finding integrals. But we should do this at least once because someone might ask you about it sometime, and it is kind of worth seeing. So what time is it? Okay, we got enough time. All right, so yeah. What I would say is this next part is not super important, but it's important for this one thing. So I know today is kind of a heavy day. I promise you it'll get less terrible than this, but sometimes you have to see the nuts and bolts before you can kind of move on to the other stuff. So here are the nuts and bolts. They're kind of ugly, but we're going to see them anyway. So I want to actually evaluate this expression, but there's a couple things I need about summations to be able to do that. So let's go ahead and grab that real quick. Yeah. And then we will come on back. I promise. Yeah. So when I write a summation like this, the sum from I equals 2 to 5 of like I squared minus 2I, what does that even mean? Oh, it's really hard to know what it means when you can't see it. Thank you. Appreciate it. What does that mean? Well, it means that I'm adding up some stuff, right? That's what this big sigma means. You add up some stuff. And you have the stuff where you start at I equals 2, and then I is called the index, which means you just let it index up to each subsequent integer until you get to the last one. And every time you index up, you add the new thing. So I'm going to start with I equals 2. So 2 squared minus 2 times 2. I'm done with 2, so now I go up to 3. So I'm going to add 3 squared minus 2 times 3. And then I go to 4. 4 squared minus 2 times 4. And then I go to 5. 5 squared minus 2 times 5. And then I go to 6. No, I don't. I stop at 5. 5 was where they said to stop. And then you could simplify that if you wanted to. I don't really want to simplify it. I actually want to point out some useful patterns here. I can break things up or rearrange things in a way that I find useful. Like I can write this as 2 squared plus 3 squared plus 4 squared plus 5 squared minus 2 times 2 plus 3 plus 4 plus 5. Which I could then write as a summation. This is the sum from I equals 2 to 5 of I squared. Minus 2 times, this is the sum from I equals 2 to 5 of I. And really the point of this is that we can see that when you have a summation of a sum or a difference, you can break it up and you can also pull out any constant multiples. So for example, without showing all this work, I could say that the sum from I equals 3 to 9 of, I don't know, I cubed plus 4I squared minus 7I, I can jump directly to saying that's the sum from I equals 3 to 9 of I cubed plus 4 times the sum from I equals 3 to 9 of I squared minus 7 times the sum from I equals 3 to 9 of I. And then, yes, if I actually want to know what that was, I would actually have to like write it out and be like, okay, that's going to be 3 cubed plus 4 cubed plus all the way to 9 cubed, which is kind of giant. And then plus 4 times 3 squared plus 4 squared all the way to 9 squared. And then minus 7 times 3 plus 4 plus all the way to 9. But that's what the summation does for you. Just a convenient way of writing a bunch of stuff added together in a certain pattern. Okay. How many more things do I need? I need like 2 more things. 2 more things? Yeah, 2 more things. So here's an easy one. Maybe 3 more things. What's the sum from I equals 1 to 7 of 5? Well, I want to be super clear here. There's nowhere to plug in the I, right? It looks less like a function, more like a constant. So when I plug in I equals 1, I get 5. When I plug in I equals 2, I get 5. When I plug in I equals 3, I get 5. And I get that how many times? Is it 6 times or 7 times? 7 times. That's kind of weird because like 7 minus 1 is 6, but then you add 1 back to get the 7. Right? There's 7 terms here, 2, 4, 6, 7. And 5 plus 5 plus 5, 7 times is going to be 7 times 5, which is 35. Or more generally, when you have the sum from I equals 1 to n of some constant, you're just adding up that constant n times. When you add something repeatedly n times, you just get n times that number. And then very, very specifically, because this is the one that actually comes up, the sum from I equals 1 to n of 1 is just n. If you add up 1 n times, you get n. Okay. One more cool trick. No, that wasn't really a trick. The next one's a cool trick. So here's a more interesting question. What is the sum from I equals 1 to 10 of I? What? I said 10, I wrote n, sorry. 10. Well, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 8 plus 9. I mean, you could do that, right? We could add that up, not too hard. But what if I said to 100? That would be able to take a little bit more, or 1 billion. So the point is there's a nice pattern. Check this out. Sure, we'll do it. No, I don't like doing it that way. I like doing it this way. So what you can do is you can add it again, but reverse it. So if I add it from 1 to 10, it's 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 2 plus 1. What's 1 plus 10? What's 2 plus 9? What's 3 plus 8? Oh, they're all 11. How many 11s do I get? I get 10 11s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is equal to 10 times 11. But I added up the thing I wanted twice. So if I want to find just what one of them adds up to, I'm going to take that, I'm going to divide it by 2. So the sum from I equals 1 to 10 of I is going to be 10 times 11 divided by 2. And in a very similar way, if I want to find the sum from I equals 1 to n, which is going to be 1 plus 2 plus 3 plus 4 plus all the way to n minus 2 plus n minus 1 plus n, I could do the same sort of trick. I could add it again, reverse it, so that each thing adds up to n plus 1. And then I would have n plus 1s, but I'd have twice as much as I needed. So I divide by 2. It's kind of cool. I think it's a really spiffy trick. Personally, I think that's really neat. All right, how much time have we got? 7 minutes, totally enough time. So back to where we were a while ago. And I will say, there's a lot more to say about summations and some other really cool patterns that I would love to talk about forever, but I don't have it forever. So I will go back to what we were talking about. So back to this. We were talking about how to figure out what this limit was. The limit as n goes to infinity of the sum from I equals 1 to n of 2 times 1 plus 3i over n plus 3 times 3 over n. And we're going to do it. So we're going to simplify the stuff first, and then we're going to break it apart into a few different summations. So first of all here, I really don't love writing the limit every time, but I should write it every time. So 2 times 1 is 2, and 2 plus 3 is 5. So I'm going to get 5 plus 2 times 3i over n is going to give me 6i over n. And that's still times 3 over n. Distributing the 3 over n, you get the limit as n goes to infinity of the sum from I equals 1 to n of 5 over 1 times 3 over n is 15 over n. And 6i over n times 3 over n is going to be 18i over n squared. Okay, I'm going to break this up into two sums. So it's going to be the limit as n goes to infinity of the sum from I equals 1 to n of 15 over n plus the sum from I equals 1 to n of 18i over n squared. Okay. Looking good. You might not believe me, but this is so I know we're looking good because each fraction, the power of n is 1 larger than the power of I. That's always what you want to happen if you're doing a problem like this. So as far as this summation is concerned, the only thing that ever changes in the summation is the index, the I or J or whatever letter they decide to use. There aren't any I's in there. So as far as this is concerned, 15 over n is a constant. So I'm adding up this constant 15 over n times. So what I'm going to get here is the limit as n goes to infinity of 15 over n times n. Plus, okay, here I've got an I, but the 18 over n squared is again considered a constant. So I can pull that out in front of the summation, just like I pulled the 2 out in front of the other summation a while ago. That's going to be 18 over n squared times the sum from I equals 1 to n of I. We're almost there, I promise. We're going to get there. We're going to get there. So then we just showed that if you add up 1 plus 2 plus 3 plus 4 plus 5 all the way to n, you get n times n plus 1 over 2. So check this out. You have the limit as n goes to infinity. Okay, 15 over n times n is just 15. And then 18 over n squared. This summation here is equal to n times n plus 1 over 2. All right, so now I've got the limit as n goes to infinity of 15 plus 18 times n plus 1 over 2n squared. Well, that's just 15. And what's the limit of this part? I know it's been a while. Let me ask you a different question. Yeah, I heard someone say, well, let me just point out. What's the limit as n goes to infinity of 2x cubed plus 5x plus 1 over 7x cubed minus 3x squared? And it should be x goes to infinity. But yeah, you guys know what I mean. 2 over 7, because you're using the fact that if you have a rational function where the degree on top and the degree on the bottom are the same, and the variable is going to infinity, the limit is just the quotient of the leading coefficients. Well, we have the same thing here, we just didn't write it out. This top part is really 18n squared plus 18. So the limit of this is going to be 18 over 2. So you end up getting 15 plus 18 over 2, which is 15 plus 9, which is 24, just like we got when we did it using the area formula. Right? We got 24 before? I mean, I think we did. We did? I'm pretty sure we did. We should have. Yeah, we did. All right. So that's kind of the big picture limit definition of the integral is that you can actually find the area under a curve, and even not just straight lines, quadratics, cubics, higher power things by using formulas like this and taking a limit. It's a giant pain, but it is something that can be done. Now, the real point here is that we're going to move past this definition and talk about the fundamental theorem of calculus and how you can actually calculate the area under the curve using an antiderivative evaluated at the endpoints. But we had to do this. Well, it's good that we did this first, so that then later on we're like, oh yeah, we saw the thing, we actually proved it, we did it once. Now we can kind of believe we're doing later on. All right, that's all I got.